In this video, I'm going to be deriving the formula for centripetal acceleration in uniform circular motion. And this is going to be a kind of geometric proof because I'm going to be using this path of the ball, let's say, along the circle, and show the derivation of the formula to you. So let's get started. Let's assume that we have a ball here and it moves along the circle with the same speed. Although it has the same speed, the direction of the velocity vectors changes all the time because it is moving in a circle. So although the magnitude of the velocity magnitude of its velocity is the same at all points, which means it has the same speed at all points, because the direction of the direction of its velocity changes all the time, that immediately tells us that there is acceleration, because if there was no acceleration, then it wouldn't change its direction. So that's why we know that there is acceleration, but we have no idea what is the formula, what's the magnitude of this acceleration, or where is it pointed at. So let's get started. Let's say we have a ball and it moves from this point to this point. That's why I've called this radius here initial radius and this radius here final radius. And this change in radius here is going to be change in radius, which is denoted as delta r. Let's say this angle is delta theta. And one important thing to notice here is that all the time, these velocity vectors are going to be perpendicular to this radiuses. And let's note that here. Yeah. And because this radius is perpendicular to this velocity vector and this radius is perpendicular to this velocity vectors, the change in angle, I mean the delta theta between these two vectors is going to be the same, is going to be delta theta. So we can show this here. Let's say this is initial velocity, which is going to be here, and this is final velocity. It's not exactly the same, but you understood. I'm sure you understood what I meant. So this angle here is going to be the same as this angle here. And in one rotation, this angle is going to be equal to 360 degrees or 2 pi radians, and it's going to do a full rotation. This vector is, if we assume this to be a vector, then this is going to do something like this and make a full rotation around the circle. And it's going to be the same with these velocity vectors as well, because these are perpendicular to each other, and because they are perpendicular, that means velocity vectors are also going to be rotating around this one circle. And we already know that the magnitude of these velocity vectors are the same. So we know that the length of this vector and the length of this vector are the same. And from the similarity of triangles, we can deduce that these two are similar triangles, because radius, of course, is a circle, so it has the same radius at all points. So radius initial radius is going to be equal to final radius, which we can denote as r, and the magnitude of the initial velocity is going to be equal to the magnitude of the final velocity, which we can denote as tangential velocity. You can notice, you can see that I did not put the vector sign here because this is not the vector, like the velocity vector. This is just going to be the magnitude of the velocity vector. So we can actually denote it as this. It's going to be equal to tangential velocity. So because these two are similar triangles, and we can make something like delta v, which means change in velocity. It's just the same thing. So change in velocity over tangential velocity. This is coming from the similarity of triangles. Change in velocity over these two, and we have denoted both of them as tangential velocity here, is going to be equal to delta r over r. So from this, we can get the formula for delta v, which is going to be equal to vt tangential velocity times delta r over r, let's say. And because this acceleration is affecting the linear velocity, we are going to use the formula of linear acceleration to derive the formula for centripetal acceleration. So normally acceleration is equal to delta v over delta t, and we already know what is delta v here. We have derived this formula for delta t, so we're going to put that here. So it's going to be equal to tangential velocity over r times change in radius over change in time. And if you notice, if you see this, you can immediately notice that if we take the limit of this as delta t goes to 0, we can see that this is actually going to be equal to dr dt, which is tangential velocity. So if we decrease this angle as much as possible, if we decrease it to infinitesimally small number, then this thing here is going to be this delta r over delta t is going to be equal to tangential velocity. So we can replace this here with tangential velocity, which will give us tangential velocity squared over r. And that is how we get the formula for centripetal acceleration in uniform circular motion.